Good afternoon, everyone. On day 5, session 9, we are honored to have with us today speaker Dr. Satendra Kumar Maurya, Assistant Professor, Department of Electrical and Electronics Engineering, BITS Pilani campus, renowned for research and academics in semiconductor materials and devices, nanoelectronics, VLSI technology. So now I will request our FDP coordinator, Mr. Rajin Singh Sikhawat, to kindly welcome her with the bouquet. Dr. Satendra Kumar Maurya is working as an assistant professor in the Department of Electrical and Electronics Engineering at BITS Pilani campus. He has received his bachelor's degree in Electronics and Communication Engineering from Madan Mohan Malviya Engineering College, Gorakhpur, India. He earned his MTech and PhD degree from NIT Kurukshetra and IIT Roorkee, respectively. His research interest includes modeling and fabrication of micro-nanoscale devices. In particular, he has done extensive work towards the development of ceramic and metal oxide-based devices for gas sensing, electroelectronics, energy storage, and electrochromic applications. He has quality publication in peer-reviewed international SCI journals of high repute with a total citation of 355. Presently, his research group is focused towards design and development of wide, ultra-wide bandgap semiconductor materials, flexible semiconductor materials, and devices for gas sensing, extreme UV detection, and energy devices. His active collaboration with CSIR CD Pilani, NPL Delhi, IIT Roorkee, IIT Patna, ISC Bangalore, OHIO State University, USA, University of California, Santa Barbara, USA. Without further any delay, let us warmly welcome to the stage Dr. Satendra Kumar Maurya, who will be sharing his expertise. Sir.
Fine. Thank you. So I would like to thank the organizing committee for providing me this opportunity to showcase my teaching and research capabilities. And here the FDP is planned towards semiconductor excellence, unveiling design and development. So basically, before coming to this FDP, I was planning what to put in my presentation and what to not. So I thought you must have been talked about various devices for different applications by so many speakers. So I thought in my presentation I should focus towards some specific fabrication steps which will definitely help the attendees to understand how to implement those designs which have already been discussed by different speakers. So in my presentation, I'll be more talking about what kind of opportunities and challenges are there in numerical modeling of IC fabrication processes. A comprehensive analysis will do. So prior to that, it is very important to discuss why IC fabrication. What is the need of IC? What is the need of devices? I mean, what is the motivation behind this kind of discussion? So when it comes the motivation part, prior to that I'll highlight the content of the presentation which we are supposed to discuss or which we are supposed to cover in next 2.5 hours. So firstly I'll be giving a brief introduction about my content. Then I'll be talking about the motivation behind this talk, and I'll also be covering the aspect of basic device fabrication processes. What kind of processes you will have to have. Either you are going to fabricate a sensing device, or you are going to fabricate any kind of energy harvester, or you are going to fabricate any kind of biosensor. Whatever device you're going to fabricate for any kind of application. So that has to be done through some basic device fabrication steps. You need to know about those steps, then only you would be able to implement your design in terms of fabrication. And I will also be highlighting in the further discussion about fabrication of CMOS inverter. It's a very simple circuitry, and all of us are surrounded by the inverters, CMOS inverters, because we all in the present era are using the digital devices, and in digital devices you will have to generate either 0 or 1. So whenever you are going to either generate zeros or 1, or a pulse or a train of zeros and 1, you will have to have some sort of digital circuitry. So that digital circuitry is known as CMOS inverter, which will enable you to generate either a pulse train of zeros or 1. Okay. So next in our discussion, I'll be focusing about the numerical modeling of oxidation processes. Although so many device fabrication processes you will have to follow in order to come up with a workable device, but practically it's not possible to cover all the devices in a single lecture, all the device fabrication processes in a single lecture. Okay, so mostly I'll be discussing about the numerical modeling aspect, the opportunities and challenges related to the oxidation process. And obviously I'll highlight first what is the oxidation process, what is the need of oxidation process, what are the limitations with the oxidation process. So I'm very sure that there would be a significant takeaway after this discussion, that you'll be in order to know why oxidation has to be done and what are the processes of oxidation, which oxide is going to be much more useful to you, which one is going to be contamination free, and what are the challenges associated with the oxidation processes and how to model it numerically. And I'll be concluding my talk at the end, and at the same time I'll also tell you the few further readings to understand other aspect of device fabrication. So this is the first slide which comes under the motivation part. Okay, so why do we need to have devices? So the basic purpose of having any device in day-to-day life is to make the life of human beings easy, first. And second, whatever technology we are developing, the ultimate goal of any technology is to contribute towards the welfare of humanity. Whether we are working in computer science, whether we are working in mechanical engineering or electronics engineering or applied physics. So the ultimate goal of any technology is how to aid the human lives, just to make it easier, comfortable, cozy, and how to contribute towards the welfare of humanity or the living beings, right? It may be animals, insects, anything on this planet. So in this context, if I will talk about, so you will see nowadays a lot of problem is arising just because of AQI. You all must be aware about that, right? Air quality index. So recently in Delhi, or if you would have gone through the today's newspaper, so you must be aware again the condition of air quality is becoming more than severe in Delhi, right? So promptly you'll have to have some solutions, right, to negate those kind of issues, or at the same time we'll have to have some monitoring system or alert system which will alert you well before in time when situation is going to be worst, right? So you will have to have some devices, right? This is one of the basic example how we are going to be dependent on devices and how the devices are going to aid in human lives or any living being's life, right? So air quality index monitoring system, and nowadays you might have gone through some literature or you might have seen somewhere, it is also known as e-nose, electronic nose. So if you want to develop an efficient e-nose, which can even detect the presence of any harmful content. It may be particulate, it may be some toxic gas, it may be some carcinogenic particulate in the atmosphere. Even if it is of the order of parts per million or parts per billion, ppm or ppb, so your device has to be much efficient so that it can detect that order of signal, right? So it could be done electronically, and if you are going to do it electronically, you will have to have some device, and if device is there, then you will have to have some fabrication approach, right, in order to fabricate those devices. So before diving into my presentation, I'll try to keep it much more interactive. Otherwise, it is going to be, a kind of burden on you. So whenever and wherever you feel like you do have any doubt, so please don't feel any hurdle in interrupting me. So just immediately and promptly interrupt me, and we'll have a discussion over it. Okay. Secondly, so many diseases are there which could be investigated invasively. Invasive approach is going on just to detect some cancer, right? We are trying to develop some probes so that we could detect so many cancers, disease, or tumor, or any other disease related to your eyes or your skin invasively, like invasive approach. We don't want to make any cut on the human body. We want to detect it through some signals. So if wherever signal is involved, you will have to have some electronic devices, right? So again, a crucial example of the devices in humans life. And apart from this, whatever I'm teaching here, whatever listeners are listening online through this live streaming of this session on YouTube, so that is also, a great example of electronic technology. And this is only possible why? Because we are having efficient devices available with us, right? Transmitter, receivers, the integrated circuit which could process these all informations, high-end processors. So in this context, you might have heard during the COVID time, there was a downtime for the semiconductor industry. And there was a huge shortage of semiconductor across the globe, right? So it was a very horrible situation for our country, because in terms of electronic devices, and particularly in terms of fabrication of devices, we are totally dependent on either TSMC, right, which is one of the largest semiconductor chip fabrication company in Taiwan, or we are heavily dependent on some companies based on US, right, like Applied Materials, Qualcomm. So these are the big players, and they are having their own monopoly in the electronics market. And the second driving force towards the development of semiconductor ecosystem is the initiative taken by the central government. Right now in the country, central government wants to be independent, Atmanirbhar Bharat, right? Self-reliant India. So in that context, by considering the situation which have already arisen during the COVID period, the semiconductor chip crunch, so India have announced its own semiconductor policy, and government of India on that time has announced investment of around 76,000 crores of money in order to give a push to the semiconductor technology. And before diving into that discussion, I would also like to quote one point which is very relevant and very important for this discussion. The point is related to the semiconductor services, the semiconductor design part. So in the design part, you'll be very happy to know the Siri Pilani, which is very next to this campus, has contributed immensely. In the Siri Pilani, uh, 2 decades back, a special semiconductor manpower development program (SMDP) was initiated. It's a brainchild of uh, the former director, Professor Chandrasekhar. And through that initiative, right now India is one of the largest producer of professionals who are giving services in the domain of IC design. So we are doing well in the design part, right? In the IC design, we are dominating the globe. Most of the CEOs, most of the semiconductor companies are being led by the Indian professionals. But we are lagging a lot in terms of fabrication. Why? Because the fab facilities are too costly. They requires a lot of budget, right? If you will go for a simple oxidation system or ion implantation system, it easily cost few crores, right? So the fab facility, firstly, they are very costly to develop, and secondly, we don't have skilled manpower. So now the government of India is taking initiative. They are considering this point. They are considering the importance of those kind of facilities, and they are coming up with different schemes. So one of the scheme they have already announced is Semicon India. So Indian Semiconductor Mission. So this event is coming under the umbrella of Indian Semiconductor Mission, where they have announced 76,000 crores investment in order to boost the ecosystem in the direction of device fabrication. Earlier we don't have. Prior to this initiative, we would be having 2-3 initiative. One of them you might have heard is INUP, Indian Nanoelectronics Users Program, INUP. This is being administrated by either IIT Bombay or IIC Bangalore earlier. Now INUP do have its centers at IIT Guwahati and at IIT Delhi as well, just to make the facilities available and accessible to every citizen of country. So they have diverted it to different geographical region of the country. So in addition to those efforts, now India is targeting and focusing towards the real fabrication of devices, right? So these are the few points why we are taking the fabrication aspect so aggressively, because we need to have skilled manpower. If skilled manpower is not there, although government is dumping few thousand crores of money, it will be a complete waste. So first of all, we need to create an ecosystem. In order to create the ecosystem, first of all, we are supposed to have the adequate and skilled manpower. Okay, so in this context, you see several other examples of electronic devices, and you must be a proud Indian after hearing the successful launch of this Chandrayaan mission, right? So whatever sensors, whatever optoelectronic devices are being used, so mostly are being fabricated and designed in the country itself, right? And obviously, of course, few of the components are being procured from either US or from Russia, but indigenously we can successfully accomplish the Chandrayaan mission. So that is one more achievement, and that is one more driving force towards taking this initiative of device fabrication in our country. And in the biomedical, a lot of opportunities are there. Nowadays, we are targeting to come up with a solution for any kind of diseases where we can do a localized treatment. If some cancerous cells are there, so instead of removing the whole part of, suppose someone is having cancer, gallbladder cancer, or someone is having cancer in any other part of body where few other vital organs are there, right? So all the time, in a conventional way, you need to open that part and you need to remove the whole part, and definitely in the process of the surgery, other organs are going to be affected. So it's better to develop some localized approach where you would be able to kill a particular cells, by sending few nanorobots. So the concept of nanorobot is only feasible when you would have a appropriate ecosystem for the fabrication of those kind of devices. Although you would be able to talk about it theoretically, or you would be able to design it theoretically, but until unless you don't have a mechanism to fabricate those devices, so it would be pointless or meaningless. So I guess all of you must be getting what I am trying to convey at this point of time. So the whole idea is, whatever theory, whatever hypothesis, or whatever science we are talking about, so that has to be feasible at the same point of time, right? So the feasibility could be analyzed in terms of availability of the fabrication opportunities. Until unless you won't be able to fabricate those devices, so it will seems quite fancy in terms of talking, like I'll design some robot, I'll design this, I'll design that, and I'll do it. So it will be a superficial kind of concept, until unless you are not having a way, you are not having proper expertise to fabricate those devices. So that's why I have planned to give this talk, in order to give you an overview how to fabricate these devices. Let us example, you want to fabricate some gas sensor, or you want to fabricate some FET based biosensors, right? So first of all, any device you will be thinking of, that has to be CMOS compatible, that has to be IoT enabled. In the present context, whatever device you are planning for, suppose you are planning for some biosensor, right, just to detect some analyte or detect some cancerous cells. Sorry. Okay, well, sorry. So it has to be feasible from the fab point of view, and you will have to have some basic idea how to do these kind of fabrication. Okay. So another motivation why to dive in further into the fabrication, whatever devices are existing today, we all are having smartwatches, we all are having smartphones. So still the hunger is to reduce the power consumption, because whatever you are developing, that has to be power efficient. If you are charging your mobile phone, so you wish to have the battery full for the lifelong, but that is not practically possible. But yeah, at the same time you will be looking for some solution where you can have everlasting battery, either in your mobile phone, either in your laptop, or in your smartwatches. At the same time, it has to be smart enough to carry. Like you are having a cell phone of 2 kilogram, so that is pointless, meaningless. So you would try to develop a cell phone which would be of the weight 10 gram, 5 gram. However, it seems quite hypothetical at this point of time, but in future when wearable and edible technologies are coming, so it is quite possible, right? At the same time, it has to be very fast in nature. Like whatever computation, whatever kind of work you are doing through your device, it has to be very fast. So for faster devices, you will have to have very short device dimensions. Means you need to do the miniaturization. Number of transistor in unit chip area has to increase. That's only you would be able to increase the speed of your device. At the same time, if you are miniaturizing the device, it means you are increasing the device integration. It means per unit area, the number of transistors are going to increase. So it will enhance the complexity in your design, right? So you will have to combat with the design issues. At the same time, if the device dimensions are shrinking down, right? So it would be very difficult to fabricate them. You might have heard about 0.25 micrometer technology or 250 nanometer technology. So we are coming from 250 nanometer to 180 nanometer, from there 90, 45. Now 3 nanometer technology nodes, transistors and processors are there in the market, right? So it's a remarkable breakthrough, and that's why you are able to talk about the 5G and 6G technologies in the present time. As the technology nodes are shrinking down, they are providing the opportunity to do the computation at a very fast rate, right? So this is the beauty of electronics, and the all beauty is possible when you would be able to fabricate your devices, whatever you are designing. So I have earlier quoted, we are doing well, and we are one of the largest producer of the design engineer across the globe. India is the country, and the major contribution is coming from Pilani. The SMDP program is the brainchild of Siri Pilani. So that has revolutionized the whole country in terms of design part. And again, Pilani, you may say, is taking a lead. Like Siri Pilani is having their fab lab, and we are also supposed to have a fab lab at BITS, supported by the DST, and that investment would be more than 100 crores. So we would also try to contribute in this desert towards the fabrication from silicon to the sand to the silicon. I mean, the basic of electronic devices existing, more than 95% devices are being fabricated out of silicon, and silicon is coming from sand, and this is a region where you will find sand everywhere. Freely available in abundance. So sand to silicon, right? So these are the few factors which are driving the whole country towards the fabrication aspect of devices, because we are doing well and we have done enough in the design aspect. Okay, so again, few points. Suppose you are fabricating any device, right? And you are a device engineer, but you don't have idea about the process variation during the fabrication. For example, thank you. For example, I'm drawing a two-dimensional cross-sectional structure of a MOS. Okay, so this kind of structure you are fabricating. Okay, and if you are not aware about the process variations, right? So there may be a situation that at the end your device is not working properly, and what may be those process variations? Like this kind of structure you are looking for, but if you are not knowing in detail about the doping process, doping may be done in two ways, either ion implantation or diffusion in the electronic devices. So if your starting wafer is p-type silicon and you are interested in fabricating the NMOS, right? So you will have to have N plus region implanted here or diffused here. You may be either getting these two regions through ion implantation or diffusion process, right? So there may be a situation, this is your gate oxide, right? This is your gate oxide, and usually it is going to be silicon dioxide, right? So there may be over diffusion. Practically we want this kind of doping profile in the source and drain regions, right? This kind of doping profile. But practically there may be this kind of profile, over doped region. The hashed region I am drawing here, that is the over doped region, right? There may be one process variation, and this gate length you have assumed to be L, the channel length, right? But what practically you are getting? Practically you are getting L dash, and L dash is much less than L. So ultimately, if you remember the diode, drain current equation ID, so you will find the presence of W by L. It is proportional to W by L. So whatever L you have designed the device for, the exact L you are not getting after the fabrication. It means process variation is happening. So if you would be aware about these process variations, like after the doping, this much of over doping will happen, right? So ultimately you will take care of the difference in channel length. Okay, so these kind of things are very important when you are going to do any fabrication, right? So the design engineer should be well versed with the fab processes, then only he or she would be able to incorporate these kind of device processing variations. Okay, and there may be a case of over etching. This is one of the processes. The second process may be the etching process. So in the etching process you will see whatever profile you would try to create, but ultimately just because of uncontrolled nature of the etching process there would be some over etching, right? So I'll also draw a picture. Suppose this is the silicon wafer and these kind of mask you are having. These are the masked region, and you want to remove the material from here and you want to create this kind of profile, right, for any purpose. The further process you must be interested to do here, the filling of oxide or creating the any well, N well, P well, right? So you are anticipating this kind of profile after the etching process. But in general, if you are doing the etching using wet chemical etching, so can you guess what kind of profile you may be getting? Do you have any other color?
Could be like you said.
Yeah, perfect. Instead of this, you will get this kind of profile, right? So initially you would have intended to do whatever processing you want. If you want to dope this region with different type of material, you want to pour some different material, you want to create some other region, right? You want to place something else, so you would have intended to do the processing in this area only. But the volume you are removing from here is something like this. It means this kind of undercut you will have to experience in your device, and ultimately that is going to impact the performance of your device, because it's all about the dimensions in semiconductor. So one of the largest enemy of semiconductor devices is the dimension variation. The second enemy of the semiconductor devices is the temperature. If you will increase the temperature, if you remember the basic carrier equation, which temperature, so it is heavily dependent on temperature. So if temperature variation is happening there, right, so the intrinsic carrier concentration in your semiconductor will vary. And third cause, the third biggest enemy for your semiconductor material is defects. If defects are happening in your semiconductor, so it may alter the performance of a device in a very uncontrolled way. You won't be able to control it. You might have heard about the surface traps in case of MOS devices, trap states in case of metal semiconductor junctions, MS junctions, right? You might have heard about Fermi level pinning in case of Schottky barrier devices. So these kind of effects do exist in the semiconductor just because of poor interface, just because of presence of surface states, right? So these things are quite challenging, and if you don't have practical exposure towards this, so you won't be able to incorporate it in your design. If you are not incorporating it, if you are not incorporating the effect of overetching, the effect of over diffusion, the effect of temperature, the effect of existence of different kind of defects in your semiconductor, so whatever design you have made using CAD tools, that may work perfectly on the software itself, but when it comes the turn of fabrication of the device and to realize the device in a lab, it won't work, because those things will definitely exist in the device when you are going to fabricate it. So that's why every design engineer has to be well versed about these variations. Okay, so these things we have already discussed. You can have a look how the undercutting is happening here in the etching process. Etching process is basically a process where we do remove the materials from the desired place, right? So you see undercutting is happening. So whatever length you are assuming here for this active area, so the length is going to be compromised. Okay, so if you are having a compromised length in a device, where do the dimensions itself exist of the order of few nanometers, and out of those few nanometers, if you are compromising fraction of nanometers, so ultimately it will impact the performance of your device in terms of current variation, in terms of voltage variation, in terms of threshold voltage variation. So many parameters are there. So before jumping to the fabrication processes, what I think it is important to understand few terminologies. If you are clear with these terminologies, so later on it will be very easy to grasp or digest whatever I am going to teach. So depending on the complexity of integrated circuit, right, we call it SSI or MSI, small scale integration. SSI stands for small scale integration. MSI stand for medium scale integration. LSI, large scale integration. VLSI, very large scale integration. And you might have heard a new terminology which is coining very well nowadays. If you could recall and tell me. USI, ultra large scale integration. So large scale integration means where you are supposed to integrate so many components together. The smallest component of any electronic device is either one transistor or one BJT. Although those are both are the transistor, our working principle is different. The FETs, the BJTs, bipolar junction transistor, where electron and hole both will contribute towards the generation of current. However, in the FETs, either holes or electron, depending whether it is N channel or P channel, whether it is enhancement mode or depletion mode, right? So working principle is different, but ultimate purpose for the field effect transistors is to provide the current, right? If you are providing current somewhere, so there may be a resistance change. If you are having a huge resistance change with respect to input and an output, so that will become the basic cause to provide the amplification, right? So whatever field effect transistors are there, they may do exist for two purposes. One is amplification and the another one is switching, 0 and 1. Sometimes it will be in on mode, it will allow the current to pass, and in some cases it will not allow the current to pass. So that will be the off state of any FET. So the FETs are basically used for two purposes, either for the switching purpose or the amplification purpose. And if your electronic device is able to perform these two purposes, so you may think of to come up with a circuit which may act as a integrated circuit where you would be able to take all these decisions together, the amplification one and the switching one. And the best example for amplification one is if you are going for the ECG, right? So the activity which is going to happen in your heart is beyond the capacity of our natural sensors. Natural sensors means we do have eyes, we do have ear, right? We do have palms to feel the temperature of any surface, but it is beyond the capacity of these natural sensors to sense what is happening there, because the signals corresponding to those variations which are happening in your heart is very small. So you need to have ECG machine. So basically in ECG machines, you have different stage of amplifiers. So whatever activity is going there, so those could be converted in the terms of electrical signals with some transducers, some transduction phenomena happens, and eventually you will be able to see some graph, right? And if the graph is coming non-linear, although we want everything in our life to be in linear, right, in a smooth way, so that is a case where we won't want to see a smooth curve, right? There we want to see a zigzag or noisy curve. If the things are coming noisy, then it's fine. If the things are coming straight, so everything is gone. Well, so that is also one of the finest example of electronics engineering and electronic devices. So when we are going to design those kind of devices, so we'll have to connect all these components together: bipolar junction transistors, FETs. In some part of your circuit we will be performing switching phenomena, 0 and 1, we will be generating zeros and 1. In some part of the circuit at the same time we will be doing the amplification, right? So this kind of circuit which is multi-purpose, which is performing several tasks simultaneously, it means in some part of the circuit, in some part of the device you will be performing the switching phenomena, in some part you will be performing the amplification. So altogether, it would be providing you solution towards any problem. The problem was to detect the variation happening in the heart, right? So ultimately, you will be able to plot the graph. You will be able to plot the functioning of the heart in terms of change of electrical signals. So altogether, you will have to use the devices in different capacities. Okay. So that's why it is known as integrated circuit. You are integrating so many things together. Thank you. You are integrating so many things together, right? So depending on the complexity of the circuits, so now I guess each and every one of you would be very much clear about the terminology integrated circuits. Why we are calling it again and again integrated circuits. Okay, so the presentation will deal with the complex processes required to make VLSI circuits. So we have designed it. If I would give an example, if I would want to only generate the chain of zeros and one of the very basic example to begin with. Suppose this kind of chain of zeros and one I'm interested to generate. Okay, and why the chain of zeros and one? Because whatever digital system we do have, right, or we have developed, so that understand only the zeros and one. If you're clicking a photograph with a digital camera, right, so it is not understanding whomsoever is standing in front. It is capturing a shape and converting all the contrast in terms of zeros and one. So whatever we are clicking, whatever we are recording, all the things are going to be stored in the form of zeros and one, because computer do understand the binary language, a pulse train of zeros and one. So ultimately, if it is understanding zeros and one, so we'll have to have some mechanism to generate zeros and one through the electronic devices. So one of the simplest example which I will quote here is, so all of you must be aware about this circuit. Hmm? This is a pull down network, this is a pull up network, this is a PMOS and MOS. The source of PMOS is connected to VDD, the drains are sorted together, and the source of this NMOS is connected to the ground, right? We are feeding input from here and we are getting output here. So this is the basic circuit. This is known as CMOS inverter. And CMOS inverter, the working in itself requires a lot of discussion. If you will be applying 0 here, you will get 1 here. If you will apply 1 here, you will get 0. So it is a 1-0 converter kind of thing, right? So depending on the amplitude of your input signal, you will be setting some threshold. Somewhere if you are observing some variation in any part of body and you want to convert it into an equivalent electrical signal, so suppose that threshold is coming below 25 millivolt. So you will set it to 0. Whatever is being detected by your electronic device, if it is less than 2.5 millivolt or whatever threshold you are keeping there, so it will be known as a 0 or as a 1 for your electronic circuit. So you have designed this circuit, but eventually you will have to fabricate it. Otherwise, it will look good only from the design point of view. You are designing, you are talking virtually, until unless you won't be able to fabricate it and realize it on a chip. Okay, so the most of the content which I'm supposed to discuss here is pertaining to the practical aspect of fabrication. What kind of challenges, sorry. Yeah, so practical aspect of fabrication. So I guess now you'll be able to catch up with all these terminologies: MSI, LSI, VLSI, and integrated circuits, right? So this is a typical slide which I have included to give you an overview about the evolution of this microelectronics technology, right? So initially, single transistor was invented by Bardeen and group in 1947, and you see down the line 70 or 75 years, now we are able to come up with the different versions of the transistors. Initially they have invented the, do you have any idea which one is being invented first, BJT or MOSFET? BJT. Well, true, but MOSFET do have a lot of application than BJT. Why? Yeah, easy to fabricate. Yeah, true. It's very easy to fabricate. It consumes less power. At the same time, it is having a very high speed. Negative temperature coefficient, yeah. So so many regions are there, right? So you see, the basic purpose of this slide is to give you an intuition about the integration of such components. So now in the present times, we would be able to integrate more than billion number of transistors in a very tiny space, right? And that is being already predicted by Morse, who is no more with us. I think in the last month he passed away, Gordon Moore. So he gave a kind of observation in kind of Moore's law. So the Moore's law predicted like in every 18 months number of transistors are going to be doubled. So since 1947 his law was valid till last few years, but now Gordon Moore is no more with us and his law is as well no more valid. And the basic reason is we are reaching towards the subatomic level. If the dimensions we will keep on reducing further, so we are reaching towards the subatomic range. So in the subatomic regime, we won't be able to control each electron and each holes and the nucleus particles. So that's why his law is no more valid. So we are coming up with some different strategies. You might have heard about the multiple fin MOSFET, FinFETs, tunneling field effect transistors, right? Gate all around devices. So different approaches we are adopting in order to minimize the power losses, in order to make the devices much more fast, in order to make devices less power consuming. Okay. So VLSI is an implementation technology for electronic circuitry for analog or digital applications, right? So the core discussion which I am supposed to have here is related to the VLSI technology itself, and it's all about the semiconductor itself, because whatever we are talking here about, either from the designing point of view or from the device point of view, ultimately you will have to have a semiconductor material with you. If you are having the semiconductor material, then only all these content would be possible or would be feasible. If you don't have the semiconductor available with you, you won't be able to do it. Whatever we will talk about, so that is going to be quite superficial. So the Moore's law I have already talked about. So what is silicon chip? I guess I have already done the discussion. Yeah. So as of now, you are aware about the integrated circuits, about the different terminologies. Now it's time to discuss about fabrication technology. So silicon of extremely high purity is required, because if you will talk about the silicon, so silicon do exist in different grades. The electronic grade silicon, the metallurgical grade silicon. So whenever you will talk about the devices, whenever you will talk about the application of the sand in electronics, so it has to be of electronic grade. Okay. So out of the sand, the first step, how to begin with. You are having sand, and that is not a cup of tea for all of us. If we are going to do any research in the field of electronics or devices, so we are having ample of suppliers who will supply you the electronic grade wafers. Just for understanding purpose, I am telling, from the sand, the silicon is prepared, the silicon wafers, better to say, of electronic grade, where you would have a very controlled, defect density. Because defects is one of the biggest enemy I have already earlier talked about. So if defect is prevailing in your wafer, so you won't be able to come up with any working device out of the wafer. Although you will do all sort of fabrication, you will continue all the processes, you will have a physical structure, but electronically that structure won't have any meaning. That would be similar to a dead body. A dead body do have all the features, hand, ear, eyes, but dead body won't be able to respond. So likewise, if you are having a device fabricated out of a faulty wafer, in the wafer where you do have a very high defect density, right? So the device will look physically, but it won't be able to work electronically. It will be dead in other sense. So you will have silicon. From the silicon you will process and get a wafer, and then you will have to clean the wafer. Although we are getting the wafer from the industries, so you'll have to clean it up, and on each wafer you will have to fabricate whatever circuits we have talked about. So one basic circuit I have talked about is the CMOS inverter. So you will have to see the CMOS inverter, you need to design its layout, and then you need to transfer it on the wafer. So this is again in the continuation about the need of these devices. We have already talked about what is the need of BJT or MOSFET, which one is faster, which one is slower. So yeah, the core content of the discussion will start from here. So if I guess you all must have attended all the previous sessions. So there someone must have talked about biosensor, someone must have talked about flexible devices, someone must have talked about the oxide based semiconductor devices for gas sensing. So if any device is coming into picture, so as a thumb rule, you need to be very clear, you need to have a crystal clear thought how to fabricate it. Until unless you won't be able to fabricate it, so there won't be any point of talking about its feasibility. Everything will look very fancy in the theory itself. Hypothetically, you may go up to fewing STEM, but until unless you don't have the expertise, you don't have the instrumentation to go beyond that dimension, so it's meaningless. So typically, I have included a picture of a fab lab. A fab lab look like this, right? And it is being termed or categorized or classified in terms of classes. Class 1000, class 100, class 10, class 10,000, you might have heard somewhere, right? If you will go to any fab foundry where a device is going to be fabricated, a chip or IC's integrated circuit is going to be fabricated, so it will look like this with a light yellow color. And there is a reason why do we have the light yellow color in the fab lab? Any one of you? Anyone from the participant? It has to be more like a discussion. Otherwise, you will take a nap somewhere. So if you will be involved, so you will feel much more connected, and I'll also get a feedback, and it will provide me, it will boost me. It will provide me some sort of energy. No, it is related to the lithography. The lithography process is also being carried out in the fab lab in order to transfer the patterns. We'll see in the further slides. So the lithography process is very prone to the UV radiations. If UV radiation is there, so the lithography process will happen. So if your fab lab would have a conventional light, so in the conventional light there may be a presence of lower wavelength or higher energy, so that may impact your photolithography process part. So just to avoid those kind of things, we would always try to have a light yellow color which is far beyond from the UV region, right? Its energy is quite low. Okay, and classes, it means as of now you would be having a brief idea about the enemies to the semiconductors. 3-4 enemies I have counted: temperature, defects, and one more enemy I have talked about: dimensions, the variations in dimensions. So defects we cannot control if we are going to do all these fabrication in open ambient. In open ambient, uh, as in the very beginning I have talked about AQI. So AQI is being measured in terms of the dimensions of the particulates, PM 2.5, PM10, right? Particulate matter size. So if the dimension of your particulate which is present in your air is significantly large, of the order of few micrometer, so definitely during your fabrication process, whenever you are doing these processes in open air, suppose I am having a piece of silicon here, right? I'm exposing it, I'm doing an implantation, I'm creating some doped region. So suppose it is P-type silicon, I'm creating N plus region, right, side by sides to make a NMOS. So during the process, I'll have to open some window in order to dope it, right? If I am doing this process in open ambient, so whatever particulates are present here, so there would be a very huge possibility all those particulates will get incorporated in your device. So if these kind of particulates are going to sit in your device, so just imagine how harmful it may be towards the performance of device. Because if you see fundamentally, Rajesh, I don't. Eh? Okay. Oh yes. Okay. So well, for example, the typical doping density, when we want to get, it's a very fundamental. Suppose we are having intrinsic type of silicon. Is it visible to everyone? We are having intrinsic silicon. We want to make it either P type or N type. Okay. So we want to make P type or N type silicon. So what has to be the doping density? Number of atoms. Suppose we want to create a doped region of N type or P type in an intrinsic silicon. So the doping density has to be 10 to the power 16 typical doping density per centimeter cube. For intrinsic silicon, the electrons and hole concentration happens to be of the order of 10 to the power 10 per centimeter cube. Again, you need to mention the temperature at room temperature. So at room temperature, the typical intrinsic carrier concentration in context to silicon happens to be of the order of 10 to the power 10 per centimeter cube. And if we want to dope it of the order of 10 to the power 16 per centimeter cube, so typical atoms, the foreign atoms would be of the order of 10 to the power 6 per centimeter cube. Why? Because in the lattice, you will see the typical density on the lattice point for the silicon atom, which is diamond cubic in nature. If you look at the crystal behavior of the silicon, so silicon happens to be diamond cubic with a packing fraction of 34%. So packing fraction for the silicon is 34%. It means 64% space is in terms of voids in silicon. Okay, and out of these 34% occupied state, it would have 10 to the power 22 atoms per centimeter cube. So if these number of atoms are there and you want to have this conductivity, so typically the foreign atom concentration would be of the order of 10 to the power 6 per centimeter cube. So it's a very general intuition if you want to make it conducting. So out of 10 to the power 2, you will be having a space for 10 to the power 6 atom per centimeter cube. It means if you are not controlling the dopant in this regime of this order, so you won't have a controlled conductivity in your semiconductor, right? So now you will be able to connect with my point. If you are doing all the fabrication in open space, right? So how many number of particulates are going to be there? First of all, whether they are dopant, donor type or acceptor type, you won't be able to control. You will be able to control the acceptor nature or donor nature when you are knowing which kind of dopant you are going to dump into the silicon, right? Either nitrogen or phosphorus or boron or aluminum. If you are aware about these dopants, then you are knowing, yeah, one of them may be donor type or acceptor type. So by doing the fabrication in an open atmosphere, you won't be aware about this. Anytime oxygen may incorporate, anytime suppose if your fab lab where you are doing the fabrication is near to any washroom, so ammonia may be there in a very huge concentration. So you won't be able to control the incoming foreign atom first. And secondly, you won't be able to control their concentration. If both the things are not in your control, so whatever semiconductor you are getting, that will be of no use. Okay, that's point I was trying to make. So just in order to ensure the proper control of dopant atom and its concentration, you will have to carry out the whole process in a closed ambient, and that ambient is being characterized in terms of classes. If class 10 clean room is there, it means the particulate which would have dimension, right, less than 0.5 micrometer would be 10 number of particulates in per cubic volume, per feet cubic volume. In 1 per feet cubic volume, you won't have less than 10 such atoms. So now you think means how a precise control on the foreign atoms you do have, right? So just to achieve this kind of control, you will have to have many HEPA filters, right, in a fab lab, and in itself it will cost few crores to maintain such kind of setup. That's why the fab based research, the fab based industries as of now are negligible in our country, but now both the government as well as private players are pushing it. As I have already quoted the example of investment or announcement of Government of India, at the same time, Vedanta Group has already announced investment of around 2 lakhs crores, 2 lakh crores in this domain, just to set up the fab and foundry. So in any foundry, if you will go, you will find this kind of clean rooms, and clean rooms are being characterized in terms of classes. So whatever advanced fabrication are happening, that has to happen in class 10, where you would have presence of foreign particles or particulates in a very controlled way. Okay. And secondly, if you are entering the fab lab, the light ambient we have talked about, the control of particulate we have talked about. The third thing which is very important is what kind of equipment you will find. So you will find wet bench, you will find oxidation furnaces, you will find glove box, lithography system, doping system, etching system, and deposition system. So we'll see sequentially why these things are being put there and how these things together in a very rational way. There has to be a rational connectivity in order to come up with a device. So I will take example how to fabricate a typical device, and there I will show you how these things are going to be utilized and in what sequence. They will have to be used in a proper sequence to come up with a workable device. So this is a typical glove box, right? You will enter in any fab lab. So you will see here, you see the glove box is encapsulated from all the other side. Two working hands are looking out. They are just calling you to come and use me and try to do some work. So you see one scientist is sitting there. So these working hands, you will insert your hand inside the chamber, and whatever fabrication you want to do, you would be able to do in a controlled ambient. So inside the gloves box, you would be able to control the ambient. Either you may do it in the inert atmosphere or in nitrogen ambient. Okay, so it's a typical example of the system present in fab lab. So now it is very important to talk about steps for device fabrication. So these are the typical steps. So we'll see one by one, and I'm very sure after winding it up, you'll be able to speak up about the fabrication of any device if I'm going to ask, right? So first of all, what you need to have a wafer, silicon wafer, right? So for the silicon wafer, you will have to have some technology to grow it from the sand to silicon. I'll be having a photograph, I'll discuss about that. So crystal growth, it means you will have a silicon first. On that silicon which you are having, you may have some sort of impurities, a residue of impurities. It may be organic or inorganic in nature. So you'll have to clean it by wafer cleaning approaches. So you might have heard about RCA cleaning procedure. We have already developed in our lab, and in any fab lab, if you go, you will find it. So RCA cleaning basically stands for Radio Corporation of America, and it's a set of cleaning, RCA1 and RCA2. One is being used to remove organic residues, and one process is being used to remove inorganic residue. So even if in your institute, if you are planning for any research, so what I will advise, you should try to develop these RCA1 and RCA2 cleaning procedure. This will be very useful to remove any organic and inorganic related issues from top of your wafer, which you must be purchasing from some vendor, right? And then as a thumb rule, you will have to oxidize it. Before doing any processing, you will have to oxidize it. Why to oxidize it? Because you will be interested to fabricate your device in a particular area. So rest of the area has to be insulated, has to be separated from the rest of the part, right? So as a thumb rule, whenever you are getting any wafer, you need to oxidize it. And to oxidize it, you need to have an oxidation furnace. Okay, in oxidation furnace, you will pass oxygen in presence of temperature. So silicon do have a very great affinity to form silicon dioxide on its top. It is very responsive, or it is very affectionate towards oxygen. Like wherever it will see oxygen, it will say, come and just combine with me, right? So silicon dioxide formation. Then in the third step, you will have to do the lithography process in order to transfer the pattern what you want to grow on your wafer. So you'll be doing the lithography process. In the lithography process, wherever you want to develop the device, right? So from there you need to remove the material in order to open the window. So at the same time, you will have to do the etching process. Once you are done with etching, you will have to do the doping process. Why doping? I will take an example and clarify. And then metallization and packaging. Okay. So now I'm going to take a very simple example about which, if you are coming from the electronics background, so you must be aware. I'm going to take a case of normal PN junction diode, how to fabricate it, and how all these processes see. So more or less, these are the generic processes which you will find in any fab lab. If you will enter in any fab lab, so all these equipments will be available to you. And now it's up to you, right? Out of these available sophisticated fab facility, whichever are required, and that is totally dependent on your device type, whether you are fabricating a Schottky diode, or you are fabricating a PN junction, or you are fabricating a MOSFET, right? So more or less these will be utilized, and the sequence will also be same more or less, right? There may be a slight variation in the sequence. This one. So it's a generic question. Have you ever seen any metallization setup? Any one of you?
We already visited a CD lab.
Okay, so how many setups have you seen?
It is like web cleaning, web control, oxidation.
So I think this discussion is going to be much more interactive then. If you would have visited the CSIR CD Fab Lab, so most of the things you would have seen there, right? And if you find it too fast, then you can just stop me anywhere.
So I have a question in oxidation part. So in that CD we saw two types of oxidation method.
Uh-huh.
One was wet and dry. So they told about the dry process is little bit. I think so. They told it is a fast process.
Dry oxidation.
Sorry, it is a slow process, but it's a very beneficial. Means their result is good in comparison to the wet part.
Yeah.
So why? What the difference we could assume in both cases?
So I'll be talking about in very detail, because the purpose of this talk is to come up with numerical models. Whatever I'll be talking as of now is a kind of intuitive idea. I'm giving you intuitive idea, but later on I'll have a discussion on the oxidation process itself, where I will talk in a very comprehensive way how to develop a numerical approach to predict the thickness growth If you are running your furnace for 10 hours, so what may be the tentative oxide thickness which you are going to have, and which method you are supposed to follow, whether the wet oxidation or dry oxidation. So I'll come to your question, but after half an hour, I guess. Okay. Okay. So the basic structure of a PN junction diode, all of you must be aware about. Right? This is the very basic structure of a PN junction diode. Am I correct? This is going to be W, depletion width. So few questions we may discuss before proceeding towards its fabrication. Will it be possible to measure it experimentally or practically? If I'll connect a voltmeter, will it be possible to measure this potential drop existing here? We in few things. And what about the Fermi level in the device? If you're having any background, if you're having any background of semiconductor materials and devices, then we may talk. Yeah. So what about the V in? Will it be possible to measure it experimentally if I'm going to connect a voltmeter across it? Hmm? Will it be possible to measure it experimentally?
By using the forward bias.
If you're going to do a forward bias, then how? What is happening? Can you please fix it? Yeah, perfect. So it's not possibly to, measure it using a voltmeter. It's an internal contact potential, right? So whenever you will plug in your voltmeter, so two contact drops will happen across this structure and eventually you will get a zero reading. So V in the cut-in voltage, you won't be able to potential drop which is happening just because of uh, diffusion of carrier from P to N side and N to P side, you won't be able to measure it. Because initially you will create the region, so it will feel the deficiency of hole, it will feel the deficiency of electron, and diffusion will happen limited by this V in. V in will exist and the diffusion will cease down. Okay. So the major discussion which we are supposed to have is how to fabricate it, right? So what you will be doing, you will take either P type or N type silicon in starting. So assume you are taking P type silicon. Okay. And as you are taking the silicon wafer, you must have procured it from some vendor. So there may be a possibility of organic or inorganic residues on the top. And at the same time, you should be aware about the dimensions. So typically, the thickness, this is the cross-sectional view. Like if you would have seen ever the silicon wafer, it happens to be in the form of a disk. So just assume I am rotating it and it is happening in the form of disk. So you are seeing the disk from this side, from the cross-section side. So from the top, it would have a surface area. So from the cross-section, you are seeing it, right? So on the top, on the cross-sectional area, you may have some residues. So you'll be removing those residues with the help of organic or inorganic etchant, which is RCA1 or RCA2 procedure. And what about the cross-sectional thickness of the wafer? Usually it happens to be of the order of 500 micrometer thick. 500, 300, depending on the requirement, 250 micrometer as well. So once you will got it from the vendor, you will clean it. In the next process, what you will do, you will oxidize it. Now on the top, you will be having SiO2 followed by your p-type silicon. Okay. In the very next step, what you need to do, you need to create a pattern in which region you want to fabricate the p-n junction. So using some mask and lithography process, which I'll tell in the later slide. So now you are having your p-type material, on top of it oxide, on top of it you will deposit photoresist, and top of it you will place a mask and you will expose it if you are doing to go the photolithography, right? So suppose your photoresist is positive in nature, positive photoresist, so you will be shining UV light from the top, and after this process you will have to etch, you will have to etch the structure in order to get an active area. So here the oxide will reside, here the oxide will reside, this is your oxide, this is your oxide, this is p-type silicon, and this is the active area of silicon which you have exposed following the lithography, oxidation, following the oxidation, lithography and etching process. So now you are supposed to create an region over here. So what you need to do, you need to do the doping part, right? So here you will dope it to make n-type, locally n-type, right? So this kind of n-type region you may create over here. So after this process of doping, right, your structure will look like this. P-type silicon locally doped with n-type material, and this is oxide and this is oxide, SiO2. ठीक है? So at the same time, I may ask, why it's a need to, do a complicated processing? Is it not very easy? Don't you think, like you take a p-type material and you take a n-type material and glue them together? It's very simple. So if it is so simple, because your vendor may provide you p-type wafer and n-type wafer separately. So take those two wafer and use some electronic glue and glue them together to make the p-n junction. Why are we following so sophisticated, fabrication steps? So do you have any answer for that? Any thought, random thought, whichever is coming in your mind?
According to you, it's only arc is possible.
Hmm?
Arcing is the welding होती है ना वही possible है दम वगैरह तो ऐसा तो कुछ आएगा नहीं.
Suppose I'm saying some. नहीं होते हैं ना electronic glue. Are you aware about electronic glue? You might have heard about silver paste. Silver pasting. Silver paste. Yeah, epoxy. It is already being do exist in the form of a liquid, the silver in the liquid state. So low silver को चिपका दो, हो गया PN junction. Is it possible to do it? Any one of you? Why? If electronically it will be of no use. If you remember the initial statement I have made, the surface states. So if you are going to glue it together, so you would have a lot of surface states. So if surface states do exist in any electronic device, okay. Is it fine? Okay. So if electronically you want to make it perfect, so you cannot, you know, you cannot afford to have so many defects at the surface. So this is going to be the P surface, this is going to be the N surface. When you are joining them together through some electronic glue, for example, the epoxy based silver paste, right? So there you would have a lot of surface states. So if surface states do exist in your device, so it will create a lot of problem to the electronic states, electronic structures, electronic bands. Thank you. Right. So we cannot do it physically. So you'll have to follow this process. So now we are very close to fabricate a PN junction. Right. So after following this doping process, so this doping could be done in two ways. An implantation or so you might have seen these setups in Siri, right? So whomsoever is available, you can utilize them. You can create the doped region. Now, once doped region is available to you, what next is required, and that is very critical. That is very important to you, because whatever device you are developing, ultimately you have a need to connect it with the external world, right? So if you want to connect it with external world, then you will have to have some contacts. And again, here it becomes very important to understand whatever semiconductor based devices you are developing, if you are not having the perfect metallic contacts which are ohmic in nature, so you cannot imagine about bidirectional transport of carriers. So just to ensure the bidirectional transport of carrier, whatever contacts you are going to develop, that has to be perfectly ohmic in nature. So make a note of it. The contact do exist in two kind. One is ohmic in nature and another one is Schottky in nature. So if you are growing any metallic contact on top of semiconductor, so by default it will be of Schottky type, right? And deliberately you will have to do further processing to make it ohmic. Schottky means it will allow the carrier to flow in one direction only, and ohmic means it will allow the carrier to flow in both the directions. So bidirectional transport has to be there if you want to use the device without any interruption. Okay, so next you will be doing metallization, right? So after metallization, you will get something like this. This is your metal, right? And back metallization again you will have to do because you want to have the contact from both sides. Here also you have metallization, and this is going to be ohmic in nature, and this also has to be ohmic in nature, right? So one contact you will get from here and one contact you will get from here. This is your p-type silicon you have started with. You have doped N region, and for further simpler view of this device, you may dice it like this. If you will dice it like this, if you will cut it like this, so eventually it is nothing but it is a kind of two-terminal device where you are having N region, P region, top contact and bottom contact. So for simpler view of this cross-sectional cut, you may draw it like this. You are having N region, you are having P region, you are having back metallization, you are having top metallization. And further you may package it, right? This is metallic contact. This is metallic contact. After slicing it, it will look like this. So this is so simple to fabricate a PN junction. So now you can just imagine, and you would be able to realize at the same time in what sequence these processes has to be followed. So first of all, you need to clean the wafer. That's why I have written there wafer cleaning. Prior to that, you will have to have a wafer. So that is not your cup of tea. You will get the wafer, ready-made wafer from any vendor. Once you have done the cleaning, by default, you will have to do the oxidation. And why to do the oxidation? Because a part, a area from your wafer you want to realize the device, not the whole wafer you are going to make use of, right? So in order to make the efficient use or utilization of the area available on the wafer, you will have to do the oxidation. Okay. And then you need to open a window in a very selective manner. So in order to open the window in a very selective manner, you will have to do the lithography, right? It means by the process of lithography, you will define the active area, in which active area of your wafer you want to do this fabrication. Because if you look from the top, your wafer look like this, right? If you look from the top, your wafer will look like this. So suppose you are working here, right? So you would want to keep all the other part, all other area of the wafer isolated or insulated, so that during the processing, these available areas are not going to be affected. So that's why, as a thumb rule, you will oxidize the whole wafer, you will open a window, and you will do the fabrication processing in this particular area only, so that rest of the area you would be able to utilize further. Is it clear to everyone? Yeah. So you will have to open a window, and through that window, you will have to create N region, because the starting wafer was P type, right? Once you have created the N region over here, so now you will have a feel that you are having a PN junction, right? And whatever depletion width do exist there, that will happen automatically. You won't have any control on that, right? It is being limited by the depletion width is being limited by which factors? Hmm? Ionization process. No, ionization is a process to put in the dopant, right? So once you are done with the dopant, I'm asking what are the parameters will affect the W, depletion width? Doping level. That's perfect. How much is the doping density here in the N region, which you are creating locally, that will govern what would be the W. Okay, so eventually you will be having the idea about W by controlling the doping density in N region, because the P region is already having a fixed level of doping. You have started with a P-type wafer having a particular doping level. So where the doping level you may vary the doping level in the N region, which you are doping again either by ion implantation or diffusion. Okay, so eventually what kind of PN junction you want, a thin barrier or a thick barrier, existing barrier, so you can do it. Okay, So in this process, again, you will have to do the metallization just in order to ensure the outer world connectivity of the fabricated device. And then you will slice it and then you will package it. And your PN junction will be ready for use, right? So likewise, you will think of fabricating a Schottky diode. In a Schottky diode, which step do I need to skip from here? Let me draw the structure of a Schottky diode first. M stands for metal, S stands for semiconductor, right? This is the basic structure of a Schottky diode. So, as per the discussion, would you be able to tell me which step do I need to skip from the above discussion in order to fabricate a Schottky diode? No. No. How come? Again, you are having a wafer having, a large area. So until unless you are not going to do the oxidation, it means you are utilizing the whole wafer for this process. So again, you will have to do definitely required. Metallization definitely you need to have, because without metallization, yeah. So yeah, diffusion is not required. Diffusion or ion implantation is not required. Why? You're starting wafer again, suppose type semiconductor you was using for the Schottky device fabrication. So you will be taking P-type wafer. On top of it, you will deposit the oxide. Why oxide deposition? Because you want to use a tiny area, and rest of the area you want to keep for any other application, right? Then you will again have to do the photolithography just to open a window and to work there. Once you have opened the window, so now you have no need to create this N region, because see, your semiconductor is now in direct contact with metal. So what you will be doing after this process, you will skip the whole process and you will directly come to metallization part. You will do the metallization from the top as well as you will do the metallization from the bottom. Yeah, additional doping. The semiconductor you are taking care of is already P-type, okay, or it may be N-type. Yeah. So now tell me, out of these two metallic contacts, which has to be ohmic and which has to be Schottky? These things are very critical and sometimes we avoid it. We should have a very crystal clear, view on this particular aspect. So out of these two contacts, which has to be ohmic, either both has to be ohmic or both has to be Schottky, or one has to be ohmic, one has to be Schottky. Any thought? Yeah, perfect. This has to be ohmic, and deliberately we would try this one to be Schottky, right? And rest of the things you may be knowing about the Schottky diode, like it would have a very high operating speed, would result a very low power dissipation, right, compared to the PN junction. So advantages you must be knowing about the Schottky diode. So this is a way like you can fabricate, and even if for the fabrication of Schottky diode, right, you need to have only the metallization unit. And photolithography and masking, these are the very basic kind of facility which you can develop at your end, right? So Schottky based diodes, if you would be able to fabricate, so the now story starts about its application. If you are fabricating a Schottky diode based structure, so you may use it for the gas sensing first. Secondly, you may use it for photo sensing application, right? How come? I'll give a small example, a very simple one. Yeah, yeah. We have already fabricated and we are demonstrating it. Up to a few micrometers, we are able to control. Like if you will ask me for the uh, photo detection application. So in photo detection, the separation between interdigitated electrode should be as low as possible, because whatever electron and hole pairs are being generated as a result of interaction of your light with the active material, it has to be swapped out immediately, otherwise they will recombine, right? So if you are having the high-end lithography system, so even if you would be able to control it in few hundred of nanometers, so if that is not the case, so you may use shadow mask, and with the help of shadow mask you may go up to 5 micrometer, precise control up to 5 to 7 micrometer, even if using the shadow masking. So suppose this is the cross-sectional view of your device, right? Suppose you are having a new material, right? Like reduced graphene oxide, and you want to use it for any sensing application. So just take a wafer, on top of it, deposit the reduced graphene oxide using spin coating or any other technique, or CVD process if you do have, or autoclave, hydrothermal, whatever process, Sol-Gel process. Just get it deposited. On top of it, you may have two electrodes. Make one of them ohmic in nature, make one of them Schottky in nature, by just playing with the processing parameters. And now you may connect it, just expose the gas, you will get the sensing signals through measurement unit. Suppose you are available with PTLA 2450. So you can source it, you can measure it, right? And whatever analyte you want to expose here, you may expose it. So the first part of my discussion, I can, we are still having time. I was just checking about the time. So first part of the discussion, I could finish. So see further, I just told you that I'll demonstrate one slide on how to get the wafer, right? So this is a typical process of growing electronic grade single crystal silicon. And why do we need to have the crystalline silicon? Do you have any idea about it? Before starting with any device processing, why do we need to have the crystalline silicon? We need to have a crystalline silicon because in the crystalline wafer, the atoms of silicons are arranged in a very regular fashion. So atomic arrangement of material is in a regular fashion, so it will yield controlled electrical characteristics like its mobility, its resistivity, its conductivity, and its dielectric strength would be isotropic in nature. It means in all the direction of your wafer, you will get a controlled and repeatable electrical characteristics, which is essentially important in order to fabricate a reliable device. Suppose you are having a wafer, right? And in one region of wafer, the conductivity is different. In another region of the wafer, the conductivity is different. Mobility is changing. So it will be very difficult and complex to come up with a working device out of that particular wafer. So that's why we need to have a crystalline material. Crystalline material means where the atoms of that material do have a defined atomic arrangement in the 3 dimension, right? So this is the process which is known as Zagorski process, and I will not discuss much about the CJET process because in itself it needs a complete lecture to discuss about it. So just for the information purpose, I kept this slide here. So by using the CZ process, you can grow the crystalline single crystalline silicon. And usually you will see silicon 100 is used for the MOS fabrication, and silicon 111, and whatever I am saying 100 and 111, these are the Miller indices, right? So silicon having Miller indices 100 is used for the MOS fabrication, and silicon having Miller indices 111 is for used frequently for the BJT fabrication, and there is and the reason is in silicon 100 you will find the surface atom density is least. Surface atom density, it means across the 100 plane, if you will calculate the number of atoms happening on that plane. Suppose the platform I'm standing in is 100 platform. This is a plane, right? 2D plane. So in this plane, if 50 atoms are there, and if I would try to move around, so I'll have to encounter, or I would have a possibility to encounter maximum number of atoms, right? True. At the same time, if this plane has 10 number of atoms, so I would have better opportunity to move around without any collision. So likewise, if your device is surface transport device, MOS is basically surface transport device. You would have your drain there, you would have your source here, in between you will have your gate, and underneath you will have gate oxide, and from source to drain, the electron will transport. That happens. It means if electron is transporting across the surface, so what wafer you would try to choose? You would try to choose a wafer where the electrons would have least possibility to face any encounter by surface atoms. At the same time, if you will calculate the surface atomic density in 111, silicon 111, you will find it is just double to that of silicon 100, right? So that's why we try to avoid silicon 111 in respect to silicon 100 for MOS fabrication. However, the planar density, the interplanar spacing in case of silicon 111 is much better than silicon 100. So that is the reason why we do prefer the silicon 111 for BGT fabrication, right? Because it's a bulk transport device. It's a bipolar device. Electrons and hole both are taking part in current transport. Okay. So as per the need, you will grow the wafer by this process, CJ process, Vygotsky process. It's a well-established process in microelectronic fabrication. And one more important picture I have included here is the picture of wafer you will get out of this process. So this kind of ingot, are you able to see this structure? This ingot, cylindrical structure. So in the form of cylindrical ingot, you will get the silicon. And from here you need to slice it. You need to slice it in the form of disc. And the disc will eventually look like this, right? So if disc is having a flat cut like this, it is a kind of indication, because suppose you are entering in fab lab, you are having 4 or 5 types of wafers, right? N type, P type, and out of N type, P type, there is a 100 orientation, 111 orientation. So will it be practically possible all the time for you to distinguish these wafers by conducting some experiment? You won't be able to do it. Like 4 wafers are having, all are looking of similar color, gray color, which is a universal color for silicon. So you won't be able to distinguish which one is P type or N type. ऐसा नहीं होगा कि P type वाला पीला दिखेगा, N type वाला नीला दिखेगा. It won't be the same. Every silicon will look very similar in color, very similar in appearance. Then in fab industries, for the ease of users, they usually give a cut, right? If this kind of single cut is there, it means it is P type 111. If these kind of 2 cuts at 45 degree do exist, it is N type 111. If these kind of 2 cuts at 90 degree do exist, it is a indication for P type 100. If these 2 cuts at 135 degree do exist, it is a indication of N type 100, right? So by seeing the bare wafer, you would be able to identify it. Otherwise, what may be the way? The other way to identify wafer is whether it is N type, P type, or orientation. So the conductivity type you may check with the help of Hall measurement. You will have to take a piece out of this wafer, you need to cut it, dice it, and you need to go on the Hall measurement setup. And using the Hall measurement setup, you will be able to identify whether it is N type or P type. So again, it is going to make your task very difficult, right? And how to confirm the orientation? Anyone? Suppose करो आपने पता कर लिया N type है, P type है. How to confirm the orientation? No. Suppose I'm cutting a piece, square piece from here, and I'm again cutting a square piece from here, right? Both P type 100 and P type 111. I'm cutting a square shape from here of 1 by 1 centimeter and a square shape from here by 1 by 1 centimeter. And then I'm giving it to you. Distinguish which one is P type 11, which one is P type 100. Will it be possible? No, not possible. So what equipment you may need to use on that time? You will have to do the XRD analysis, X-ray diffraction analysis, right? So X-ray diffractometer is an instrument which tells us about the crystallinity of wafer, right? So that will only confirm whether it is 100 and 111. So just imagine the manufacturer is making your life so easy. Otherwise, after getting the wafer, you will have to conduct, you will have to do the conductivity measurement using Hall measurement. At the same time, in order to ensure its orientation, you will have to do the XRD analysis. And XRD in itself is a very sophisticated instrumentation. It costs around 2 to 3 crore to have a very simple XRD. At the same time, a simple Hall measurement system will cost around 50 lakhs. Yeah, just to identify whether it is P type or N type, right? So anyways, so these kind of information has to be with you, right? Okay. So wafer cleaning, you may also do in addition to RCA1, RCA2. This is ultrasonic acetone clean. So ultrasonic waves are helping you to clean any residue which is being stuck to surface of wafer, right? Followed by oxidation. So oxidation is usually done with a chamber by passing or either H2O vapor, H2O vapor, or dry oxygen in the chamber where the temperature would be of order of 1200 degrees centigrade, right? So here on the top of silicon, you will see the presence of silicon dioxide. So oxidation you may do in this way, and this comes under the category of dry oxidation. And you are asking a question, dry or wet oxidation. So in the wet oxidation process, you will be passing the H2O vapor, right? And in the process of dye oxidation in the same furnace where you would have a very controlled ambient, you will be passing dry oxygen. So dry oxygen process will react with the silicon wafer which you would have got through the wafer growth process in a very precise way. The rate of oxidation will be very low. However, in case of the wet oxidation process, the rate of oxidation will happen at a very faster pace. So just because of this difference in rate, whatever you have asked, right? So there may be incorporation, there may be a chance of incorporation of defects, and those defects becomes a kind of challenge for the wet oxidation process. However, in the dry oxidation process, the chances of incorporation of those defects is probably low as compared to dry oxidation process. In the wet oxidation process, the chances of incorporation of defects are high, right? Because the activation energy is just half, which is required in the process of wet oxidation. So the reaction will happen at a faster pace. Yeah, I'm coming on that. So how usually it is being done? Because in the dry oxidation process, you will be compromising in terms of growth rate. The growth rate for the dry oxidation will happen at a very slow rate. So if you want to grow a thicker oxide, if your oxide growth requirement is very limited, you want to, I mean, just see here, the oxidation which we usually do in the microelectronic fabrication, that happens for two purposes. The first purpose is for the active application. The second purpose is for passive application. So in category of active applications, the MOS device is one of the finest example. In the MOS device, how does it work? Is it clear to everyone? You will be applying a gate voltage. Underneath the gate, you are having oxide layer. Underneath the oxide, you are having a silicon, not channel all the time. You will be inducing the channel. If it is enhancement type of device, so you will be inducing the channel. So there, you are deliberately putting oxide to induce the channel, right? Let me. I'm taking the case of a MOS cap just to understand the working, right? So this is your oxide. You are applying this kind of potential. So metal, oxide, and semiconductor. So what we'll be doing by applying the appropriate potential, suppose this is p-type silicon. So when you will apply a positive voltage, accumulation of holes will happen here. So that will enable you to realize the accumulation region in a MOS device. When you will further apply, sorry, negative voltage. When you will apply a positive voltage, that will push the hole away, right? So you will be able to realize a depletion region here. And after, when your psi-s will be equals to 2 phi f, the surface potential, which happens to be here, if that surface potential happens to be 2 phi f, so electrons will be available here. And here somewhere you have source, here somewhere you have drain. So source is also N plus, drain is also N plus in case of NMOS. Now you are having a conducting channel available from source to drain. So in this way, if you will apply a potential difference between source and drain, so electron from source to drain will flow. Right? This is the basic idea behind working of a MOS device, particularly NMOS. So here you see, we don't want to experience any current transport from source to gate, right? That's why we are putting oxide here in between, the oxide layer. So this oxide layer is facilitating us to induce this channel where we may have a lot of carriers to connect both source and drain regions. At the same time, this oxide layer is facilitating or providing us a way to stop any conduction between source to gate, right? Source to gate current is ideally Ig equals to gate current equals to 0. So in this way, you see, the oxide quality would be of prime concern. The oxide, if this oxide is going to be leaky, if this oxide is supposed to have any kind of conduction through it, so will that be useful? No, not at all. If suppose the oxide is having some mobile carrier, and when you are applying different bias at gate drain source, so it will start conducting. So if it will start conducting, so the major USP for your MOS device is that its input impedance is supposed to be infinite. Ideally, not happens to be infinite, it happens to be of the order of mega ohms, right? So if some sort of conduction is happening between gate and source, so that will destroy or despoil the purpose of MOS device. It means the gate oxide has to be of very high quality. It should not conduct, and at the same time, its its dielectric constant has to be of good quality. At the same time, the defect density should not exist inside it, right? The nature has to be amorphous. Because I told in the previous discussion, just to experience better electrical characteristics like mobility and conductivity, the material has to be crystalline. So it has to be non-crystalline because we won't want to have any conduction through it. Well, so here we want this in the form of active application. Why? Because the oxide is controlling the channel. It is, deciding how much carrier has to be there in the channel. Because whatever voltage you are applying at the gate, some of the potential is dropping across the oxide Vox, and the rest of the potential is dropping across semiconductor Vs, right? And in this way, you would be able to create the channel. So these kind of application of oxide comes under the category of active application. And what about the passive application? Suppose you are extending the same wafer. This wafer you are extending like this. And you want to again fabricate another NMOS here. So there has to be some insulation between these two MOSes, right? So you might have heard about the trench formation, shallow trench isolation, right? So you may create a trench and fill the trench with the silicon dioxide, and electrically this MOS, if this is MOS number 1, will be insulated electrically from MOS number 2. The MOS number 2 won't have any electrical impact of MOS number 1 on it, right? So the passive application of oxide is this kind of passivation, right? And to provide masking during the doping process. during the lithography process. During the lithography process or during the doping process, we are using the oxide as a mask, right? Sometimes, usually in the lithography process, some other materials are being used, particularly for the masking purpose. But for the ion implantation and diffusion process, in most of the cases, silicon dioxide material is used as a mask. So masking, isolation between electrical isolation between devices, passivation of the surface, all comes under the category of passive application. And the uses of oxide as a gate oxide in most devices comes under the category of active applications. So now you will be able to realize in which case I'm supposed to use the oxide and what has to be its growth mechanism. So whenever and wherever we are targeting the oxide to use as an active oxide, so it has to be grown by dry oxidation, because in the dry oxidation we would have a least possibility of introduction of any kind of defects. And thickness has to be very low. Typically, will you be able to tell me the typical oxide thickness in MOS used in 180 nanometer technology or 250 nanometer technology node? The typical gate oxide thickness. What has to be the order? Few nanometers, 5, 10 nanometers, right? So 5, 10 nanometer is not a big challenge. Either you are going to use the dry oxidation or wet oxidation. So in the dry oxidation, if it is facilitating a better electrical property, better electrical behavior with least number of defects, so definitely you will have to go with the dry oxidation process. However, if the oxide thickness required would be 1 micrometer, so what you are telling, in that case, first of all, we would try to grow few nanometers through wet oxidation, then rest of the thickness by dry oxidation, then rest of the thickness again by wet oxidation. Dry, wet, dry, this kind of sequence is being followed. So it will ensure both the things, electrical quality of your grown oxide, as well as it will provide you an opportunity to grow the oxide in a faster way, right? So these are the typical processes, and you see, as of now, you must be feeling like if you have any way to predict or to implement all these processes numerically, so your life is going to be very easy. Suppose crystal growth, wafer cleaning, you can't control mathematically. You will have to do it, manually. But during the crystal growth process, if the whole process of crystal growth, you could have, if anyway, you could have any numerical model, like for how much time you are going to do it, at what rotation speed you are going to do it. If you will deep dive into the CJ process, so you will have to rotate the whole, crucible at some speed, right? There has to be some specific temperature. So if you could control that temperature externally, which is very easy for us by using any PID controlled heating system, right? So likewise, if we could develop some numerical model for each of the processes, so we may say that our fabrication, the overall fabrication is going to be much more controlled. Like in oxidation process, if I'm carrying out the dry oxidation at this temperature for this time, if in advance I would be able to predict the thickness, means how much thicker oxide is going to grow. So that will definitely make your life easy, because somehow you are automating the system, you are doing the automation. And if anywhere you would be able to do the automation, what you need to do, you need to give the feed, right? You need to start a button, and after the process is being done, you need to stop the button, right? In between, the process will happen automatically. That is the basic purpose of automation. And in addition to that, everything is going to happen in a very controlled way, right? So that's why in the very beginning, when the fabrication processes started happening at a industrial scale, so they have started to model all the process numerically, right? So just to discuss the numerical aspect of modeling of all the processes in a single lecture is impractical, because you will have to do a IC fabrication course of at least 40 lectures to understand the numerical modeling aspect of each processes. Like if you want to deep dive into the oxidation, deep dive into the lithography, etching, or an implantation or diffusion process, so you will have to spend at least 5 lectures on each topic to understand its numerical modeling aspect. Like what may be the universal variables there which you could tune in order to predict the doping density, doping profile. If I'm just taking a case of doping, if you are doping some region of the semiconductor, so 3 4 things may be there. What may be the doping profile? How much would be the junction depth? If you're doping something from the top, so how deep it will go, right? So junction depth. At the same time, what profile will it look elliptical? Will it look circular? Will it look error function profile, complementary error function profile, or Gaussian profile? Whatever profile or a box profile in your semiconductor. So that could be done numerically, but it needs time. So in the context to discuss the fabrication in more comprehensive way, what I could do, I have chosen the oxidation process here, just to give you an intuition how to develop the numerical model of these kind of fabrication processes, right? For the next processes, rest of the processes, you can have a self-study kind of thing, just in order to understand. So here in today's lecture, I'll be more focusing towards the oxidation. So all the aspect of oxidation we have already talked about. How should be the oxide, and whether it should be amorphous or crystalline, whether it should be defect free or it should have a defect, electrically conducting or electrically insulating, right? So at the same time, if I'll ask, what has to be the band gap for SiO2? These are the furnaces where the oxidation happens. You see, these are the commercial wafers, 12-inch wafers, which are stacked together, and they are just ready to go inside the oxidation furnace, where you can control the ambient as well as you can control the temperature, okay, inside the oxidation furnace. And one more important thing, I will tell you about the oxidation process. Then I'll start with doing the numerical modeling part, right? Batao bhai, what has to be the band gap for silicon dioxide? Yeah, around 9 electron. Perfect insulator. So see, oxidation may happen in two ways. This is your silicon wafer, right? So one way is you are growing oxide downwards. During the growth, silicon is being consumed. So after the growth of oxide, the picture will look like this, right? This whole thickness is silicon dioxide. And the other way is the oxide is growing upward. This is your. So out of these two grown oxides, which may be a good choice for electronic applications? Hmm? Second one, and Rajesh is saying first one. So why Rajesh? Why first one? Here you are compromising your silicon. Perfect. So I hope you have got the point. So what he is trying to make, initially this was our outer surface for the silicon. And we all are knowing the basic fact about the crystallography of airy material. Suppose this is the material. So this surface may be little rough. If we would have any mechanism to experience the inner surface at a depth of 2 or 3 centimeter, so that is supposed to be much more organized or smooth or having less defects. So here the point is when you are growing a crystal, right? So outer surface may have some dangling bonds. In case of silicon, silicon requires 4 atoms to satisfy its outer bonds, right? Outer cell electrons. So if we are having an oxidation mechanism where silicon is being consumed, and at the end of process you are having silicon dioxide of this width, and few part of silicon is as well consumed. It means your interface between silicon and silicon dioxide is moving inwards, right? So you are having your final interface between silicon and silicon dioxide somewhere here. So it would have less dangling bonds, less unsatisfied bonds, and dangling bonds are one of the biggest contributor towards defects, and defect is a biggest enemy of semiconductor. So one enemy we are combating through this approach. However, here the starting surface was same and the ending surface is again same. If there would be any presence of any dangling bonds related defects at the surface, so that defects will do exist between oxide and silicon. At the same time, just realize, just try to imagine, if you are going to create a source here, a drain here, right, and you are going to make it as a gate oxide, so you would try to realize the carrier transport across the surface underneath the oxide. So if defect density is higher, here in this case, so it will be difficult for the carrier to transport from source to drain. However, it is going to easy in this case because as the interface is moving inwards. So make a note of it. Only the dry oxidation process or the wet oxidation process would provide you, and dry and wet both falls under the category of thermal oxidation. So only the thermal oxidation will provide you a facility to move down the interface, to deep dive in the silicon. Although few nanometer of silicon thickness is being consumed in this process, but the added advantage you are getting in terms of less number of trap states at the interface. Here you may save few nanometer of silicon from the thickness point of view. I mean, few volume of silicon wafer, but you will have to sacrifice in terms of defect density. So if your device is surface transport device, so you cannot compromise with interface states. You will have to adopt this approach. That's the reason why in order to fabricate the MOS devices, we'll have to follow the thermal oxidation process, in particular the dry oxidation process. So these are the particular furnaces which are being used to carry out such kind of dry oxidation or wet oxidation process. Both comes under the category of thermal oxidation. Only in ingredient changes. When you are doing the dry oxidation process, you will be passing the stream of dry oxygen. And when you will be doing the wet oxidation process, you will be passing the H2O vapor. Okay. So now you during the dry oxidation process, with the silicon wafer, right? And after the process, a thickness of silicon is being consumed, right? And eventually your interface is moving somewhere here. It means your interface would be much more defect free from electronics point of view, right? So the kinetics of diffusion happens in this way, like gas, which may be oxygen or H2O vapor, will come from the left side, and your silicon will be available here through some heating element. You will be providing heating, and all will happen inside a encapsulated chamber, right? And usually that chamber going to be of quartz tube, because in the quartz itself you will find silicon dioxide, right? So these are the few basic details about the lithography process. So you must be knowing about this. I'll skip and I'll directly try to jump on the numerical, modeling part of oxidation process. So these processes must be clear to you. And CMOS fabrication and this diode fabrication we have already seen. So these are the redundant slides from that point of view. Yeah, no problem. I don't have any harm in sharing. Okay. So in the oxidation, these are the basic characteristics of the oxide grown. You must be aware about it. And this is a typical transmission electron microscope, which is revealing a crisp crystal difference between these two images. Which one is looking more patterned? Silicon one, because we want conduction in the silicon, not in the silicon dioxide. That's why the silicon dioxide is looking glassy in nature, cloudy in nature. So it is amorphous basically, right? And this is crystalline. So here you would be able to see the atom by atom arrangement of silicon. And remember, silicon do exist in the form of diamond cubic, right? With a packing fraction of 34%. Okay. So these are the typical examples and applications we have already talked about the oxides. It may be used as a masking, pad oxide, gate oxide, or field oxide, right? We have seen all those things. These are few very interesting images which is showing how it looks like experimentally. When you will do any experimental investigation cross-sectional view using scanning electron microscopy or tunneling electron microscopy, the picture will look like this. Okay. And this is all about the oxide structure. So I'll suggest you self-reading how the structure of oxide look like. But here we want the structure to be amorphous in nature for electronic application point of view. But in case of quartz, you want your silicon dioxide to be in crystalline form. And these are the typical thermal, furnaces, horizontal tube furnace, 3-zone furnace. So in all the 3 zones, you'll be able to place the substrate for oxidation purpose. And eventually you are passing in thermal oxidation either the oxygen or the H2O vapor, depending on the wet oxidation and dry oxidation. And this is a much more closer view. You see, you would be able to see the hotness of this reactor, and there you are passing. These are the disk of silicon. So they are stacked together, and the scientist is trying to pass it place it in the furnace, and then they'll be passing either dry oxygen or H2O vapor, depending on the process whether C is trying to grow in the dioxide either by the dry oxidation process or wet oxidation process. You may see a schematic view here. So these are the heating coils, and this is the ampule of quartz, and inside it we are trying to place the stack of silicon. So these vertical lines represented by red color are nothing but silicon vapor. So I'll take a pause. Huh? Time is over. How much time is left? Okay. So I'll finish soon. Okay. So these are the approaches by which once you have grown the silicon dioxide layer, so you need to measure the thickness. So these are the approaches: profilometry and ellipsometry, to measure the thickness. Basically, how much thick oxide have you grown? Okay. So after that, if you want to develop a mathematical intuition, how to predict the grown oxide thickness. So the whole process, give me 5 minutes extra, I'll finish it, right? So if you allow me, so I'll take 5 minutes extra and I'll give you a mathematical intuition, right? Happens in two ways, downward and upward, right? So we are interested in downward approach where the silicon is being consumed. Okay. So these are the two reactions: silicon dioxide producing SiO2, and silicon and H2O vapor. In case of wet oxidation, H2O vapor you will be passing actually. So during the process, if this is a silicon vapor, right? So how to generalize it? On the wafer, silicon wafer, there may or may not be a presence of native oxide, because silicon is very much prone towards oxidation. So if a thickness of silicon dioxide is being assumed, so this mathematical model is going to be more general, right? Gas will be passing from this left side, right? Whatever gas, maybe oxygen or H2O vapor, right? And eventually it will be reacting with the silicon surface in order to yield the silicon dioxide. So different concentrations I have listed here. Cg is the concentration of gaseous species or reactant, oxidant, concentration of oxidizing species in gas, concentration of oxidizing species next to gas and silicon dioxide interface, Cs. C naught is concentration of oxidizing species at outer surface of oxide, and Ci is the concentration of oxidizing species at the silicon interface, right? So just try to see three fluxes are responsible here for the oxidation process. If we want to model it numerically, the flux F1 is the flow of oxidizing species in the gas, and how much of that flux in the form of F2 is passing through this pre-existing silicon dioxide, and how much of that flux F3 is going and react with silicon. And in steady state, all these fluxes has to be equal. And you see here C star is the equilibrium concentration of oxidizing species in oxide. So what we will try to do, we will try to represent the CO and Ci in terms of C star, right? The oxidizing species flux at this interface SiO2, I mean just inside the SiO2 and just at the interface of silicon and silicon oxide, if we could anyhow represent these two C0 and Ci in terms of C star, so purpose will be solved. We would have some numerical relation between them in terms of time, right? So that we can predict the oxide grown in particular time at particular temperature. So we need to first find the flux F1. So flux F1 is nothing but the concentration gradient between Cg and Cs. Cg and Cs. Just because of this concentration gradient, the oxidizing species would try to move towards silicon dioxide and silicon interface, right? So here you will find F1, we may write Hg into Cg minus Cs, where Hg is mass gas phase mass transfer coefficient, okay? And Cg and Cs we have already defined. These are the oxidizing species concentration in gas and solid interface. And by using the basic gas law, you can represent this Cg in terms of partial pressure, right? So this transformation, this substitution, and further this partial pressure may be represented in terms of these two concentrations C naught and C of Henry's law. Why? Because eventually we want to see all the concentration, all the relations either in terms of Ci, C naught or C star. Okay. So rewriting the equation 1 which we have derived here, the equation 1, we may write it in terms of C star and C naught with the help of Henry's law. And you see now the first equation you have got, which is relating F1 and C star and C naught. Likewise, the second flux, which is flowing through the pre-existing oxide layer. So that would be governed simply by Fick's law, Fick's first law. Diffusion coefficient multiplied by the concentration difference into thickness of the oxide, pre-existing oxide. So you can generate this. And the third flux is governed by the reaction rate at this interface, silicon and silicon dioxide interface. At what pace the reaction is going to happen. So you would be able to write the third flux. And in the state of equilibrium, F1 has to be equals to F2 and has to be equals to F3. So if you will do little mathematics, you will substitute few things in all these three equations. So eventually, you will be able to represent C naught and Ci in terms of C star. You see, Ci in terms of equilibrium concentration, C naught in terms of equilibrium concentration. And if you would try to generalize it, suppose this is your silicon dioxide, somewhere here you have silicon, and this is the air from which your oxidizing species is coming, right? So you see, if your axis tending towards infinite, in case 1, if your axis tending towards infinite, what will happen? It will give you the complete intuition. If your axis tending towards infinite, what will happen? C naught will be नहीं भाई देखो D is tending to 0, D is tending, or X or you may say like X is tending towards infinite. That is very similar, na? नीचे भी तो है, so it will get cancelled actually. So C naught will become C star, right? And what about this Ci? Ci will naturally become 0. So this kind of situation will happen, and you may resemble this situation like if x is tending to infinite. So it means if diffusion coefficient is tending towards 0, it tells you that the thickness, pre-existing oxide thickness, is good enough that it is not allowing any oxidizing species to react or reach at this silicon-silicon dioxide interface. And the concentration of oxidizing species will fall down like this. It means in this case, your oxidation process will be limited by diffusion. The diffusion of oxidizing species through pre-existing oxide will dominate the process. Mathematically you are saying, and intuition wise as well. Suppose this platform is silicon, on top of it you are having sufficient good enough silicon dioxide, and now from here the oxidizing species, either dry oxygen or SU8, or would try to do a react here. So basically it will be possible. So what is the mathematics? The dot it to the metallic. It is validating whatever assumptions you have taken here in the very starting. Okay. And case 2, when D is tending to infinite, it means there won't be existence of any free oxide. X tending to 0. It means whatever concentration of oxidizing species you would have here at SiO2 and gas interface, that will be equal to Ci. Definitely possible, because physically no SiO2 here is existing. So whatever is C0, that will be equal to Ci. Okay. So by considering these 2 points and considering the basic reaction, you can write the number of reactant species coming from the left will be equal to the flux F3. F3 you have already represented Ks star upon P so many constant. Okay. And now you may integrate it with respect to distance and with respect to time. After integration, right, and putting the initial condition, because when your T is 0, so what we are assuming? We are assuming existence of xi degree, right? So if you will put T equals to 0, so xi, this will represent P. P will represent the existence or thickness of pre-existing oxide, right? And by dividing the above expression by 2D upon Ks in both sides, you will have a quadratic equation like this. So here you are having only one variable, that is x. The rest of the things are constant, either the diffusion constant or Ks or C star, right? So from here you can predict the oxide thickness. So further, if you solve it, right, and you will do substitution, so eventually your expression will look like this: x square plus ax equals to bt plus tau. Tau is the initial thickness which is existing there, t is the time, and x is the variable, means the thickness you are interested in, and a and b are constant. So this is a simple quadratic equation. If you will solve the quadratic equation, this kind of solution you will get, and this solution is nothing but the oxide thickness which you are growing with the help of thermal oxidation process. So likewise, this thermal oxidation process, you may come up with the mathematical model of ion implantation, diffusion, as well as your Zagorowski process, CJET process, or your rest of the processes we have discussed. Most of the processes you can model it mathematically, and once you do have a mathematical model, your life will become very easy. Like now you are having a wafer and you want to grow a 250 nanometer or 1 micrometer thick oxide. So just calculate the required time, required temperature, and put it, and just switch on your furnace and go to the furnace. After that many hours, you will realize the same thickness. And this model is being proposed as Deal and Grove in way back 1964. That's why, and the funniest part is still it is valid. So this model is known as Deal and Grove model, right? And there are so many shortcomings of this model which have been addressed time to time to make this model more efficient. So that's all about the numerical modeling of the processes. So I guess after this lecture, you would be having the idea. There may be few things as a takeaway. What are the exact processes which you need to follow? And what may be the setup of a clean room? What kind of facilities you are supposed to see, and how to categorize the clean room, right? Class 1000, class 100, class 10. And on top of that, if you are doing the automation, so what may be the important and potential variables for you? So for the oxidation process, the potential variables was the concentration gradient of oxidizing species at different interfaces, and how to generalize the process. If you want to develop a general mathematical model, so you will have to take, you are advised to take the most general case. You need to do the worst case analysis. What may happen in the worst case? So that's all about for today's lecture. If you want to follow the course, you will have to at least do 40 lectures to, completely understand the course on IC fabrication. So thank you very much for your cooperation and participation. If you have any questions, so you are most welcome to ask.
Like we always purchase silicon wafer from outside country. We cannot make silicon wafer in our country. Why? Because we have so many fab labs. We have uh, crores of budget for this. Why we cannot make a silicon wafer in India?
So I guess I have answered this question in the very beginning. As the technology node keep on changing, so a lot of instrumentation keep on changing time to time, right? So all the instrumentation pertaining to the fabrication costs few hundred of crores. So in the India, we were not having an initial setup towards the fabrication, right? From the very beginning. If you will go back in 80s or 90s, so that's why we were not having the setup. So instead of installing a few thousand crores of setup, it was always a good choice to purchase this from the outside. Suppose one wafer is going to cost you for $8. For $8, why you are going to invest 1,000 crores? So that was a perspective earlier, but now the narrative is changing. The India is becoming self-reliant, and in
Yes,
the same context.
that's why I have asked this question. It comes to my mind.
Yeah, that's a
That
very, very valid and good
Atmanirbhar, if we
question.
want to become Atmanirbhar, then why we are always purchasing? Not
But
even India.
but no longer we are going to purchase. Now the
And
fabs are coming.
now Moore's law, even Moore is no more.
Hmm.
Uh, we have changed the materials like flexible and other organic materials we are
Hmm.
using. Still, we cannot make a silicon wafer. We are just buying wafer.
So that was the initial reason why we have purchased all the wafer from the outside. But as fab and foundries are coming, they are showing their footprint in the country. So very soon you will be having like the assembling of iPhones is happening in Bangalore right now, right? All the parts are coming from outside, but assembling they have started. So in the same context, in the very coming time, you will see most of the ICs are being fabricated. If you are fabricating the IC, so naturally the starting material has to be the silicon wafer. So initially, wafers were procured or purchased for the laboratory purposes only. So in the lab, merely you required 100 or 200 crores wafer in a year. So for 100 and 200 crores wafer, no one is going to set up 1,000 crore,
Now,
factory.
like we buy a wafer and we do oxidation, metallization, everything. We make devices. Then it's easier to just purchase that device from other countries. Why we are investing? We are spending so much of budget just for
Just to become
processing.
the self-reliant. Just to become the self-reliant, because as you are developing technology for space, so everything you cannot purchase from the outside. Otherwise,
Even we are dependent on others, so they can refuse that we will not give
yeah,
any.
that happened during the COVID period. I have already cited this. In the COVID period, there was a huge crunch of semiconductor chips, and if you would have thought to purchase a hard disk on that time, so it was not even able. I mean, it was not possible to purchase a 1 TB or 2 TB hard disk on that time, because there was a huge crunch of semiconductor memory storage.
Even small devices were so costly, like pulse
Yeah.
oximeters and all that. Okay,
So
thank you,
we
sir.
want to be self-dependent in terms of electronics, and that's why they are coming up with a lot of investment and planning. Anything else? SOC, system on chip. So it depends on application, whether you are developing SOC for the biomedical application, whether you are lab on chip, right? Lab on chip kind of things in the bio, whether you are doing lab on, but ultimately it has to be integratable with the existing IoT enabled system and integratable CMOS technology, whatever scale. So suppose if your device is already in the 7 nanometer technology node, so it has to be compatible with the 7 nanometer technology node. Whatever latest technology node you are developing, so whatever SOC or lab on chip kind of devices, if you are developing, so it has to be compatible.
Thank you, sir.
Thank you. Thank you for your active participation.
Thank you very much, sir, for briefing about the fabrication process and the mathematical modeling for the oxidation part. So at the end, we'll request our FDP coordinator to honor our guest of our distinguished speaker with the token of love. Thank you so much,